Hello students, Jai Swaminarayan. I am Professor Urvish Mewada, HOD Electrical Department, Sri Swaminarayan Institute of Technology, Bhat, Gandhinagar. I am the subject matter of Power System 2 subject, which is in the 5th semester Electrical Engineering, and GTU subject code of this subject is 3150911. Students, we are currently discussing the chapter number 5, that is symmetrical component, and this is our lecture number 3. Students, in last lecture number 2, we have discussed certain topics related to the symmetrical components of unsymmetrical phasor, in which we have derived the voltage and the current equation for that respective phasors, and then after we have discussed the power terms of symmetrical components, in which we have discussed the relative equations of the active power, reactive power, and the apparent power, and then after we have discuss the example which are based on the symmetrical components. And today we are having a lecture number 3, in which the topic number 8 is sequence impedance of power system elements. Now if we talk about a power system, then we have a very large power system, or we can say it is an interconnected power system. Now in the interconnected power system, we consider certain sequence for the particular generating stations. Now we if we need to transfer a power an economical way, and if we do not want to face certain problems related to the short circuit or any kind of faults, then we need to keep in mind the sequence impedance, or we can say impedance of the particular elements which are present in the power system. So let us discuss the sequence impedance of the power system elements. So the main application of this theory is to of the symmetrical component is the analysis which is based on the three-phase network. Yes, we have the three-phase network in the power system, and which are subjected to the unsymmetrical fault. So as I discussed earlier in this chapter, that whenever any kind of changes of the load or switching occur, or any kind of like contingency occur, then the unsymmetrical fault generates in the power system. So in such network, the impedance of the say each phase up to the faults are say equal. So that's why for the given sequence, the ratio of the phasor sequence voltage to the phase current that we need to keep in mind is defined as the impedance to the sequence current. So when for that to determine the impedance of the phase sequence current, we need to check the phase sequence say voltage to phase current. So from that we can determine the impedance of the phase sequence, and then therefore we can say we can simplify the phase sequence impedance. Now let us discuss. We have all three sequences that we have discussed in this chapter. So the first sequence is that is the first sequence is that the positive sequence impedance. So in the positive sequence, we have an we have an element that we have derived, that is Va1, Vb1, and Vc1. So that's why the impedance is say Z1, and we know that we already know the equation of the impedance is say V upon I. So Z1 is equal to Z1 is equal to V1 upon I1, because we are discussing over here positive sequence impedance, and positive sequence is indicated with 1. Now negative sequence impedance, Z is equal to V upon I. So here for negative sequence we use the notation that is 2. So Z2 is equal to V2 by I2. Now for the zero sequence, the Z0 is equal to V0 by I0. So these are the three say impedances of all the sequences which are say generated whenever we have the unsymmetrical faults arise in the power system. Now therefore it is essential in the study to check out the behavior of the system under symmetrical fault condition. So whenever the symmetrical fault arise, all the parameters means element parameters will change. So that's why we need to check all the parameters at the time of means behavior of the all the elements at the time of fault. Now over here, the each components, whether the static, so in this we are talking about the whole power system, so in which we have all different type of elements, say static elements. So in static elements we have the transmission line, transformer, and the static load, which are connected with the power, with our power system. And or the rotating, so in rotating we have certain synchronous condenser and the say induction machine to say improve the power system, means power quality. So we have the static and rotating elements which are present in the power system, has three values of impedances. So all are working on the three phase, so all are having three values of impedances, and say one for each symmetrical component of the current. So therefore in generator the positive and negative sequence impedances are equal. So this is the most important point that we need to keep in mind. In generator, positive and negative sequence impedances are equal, but the negative sequence are slightly less than the positive sequence. So this is the main point to determine the sequence impedance of the power system. Now in the static device, say positive and the this is the rotating device. Now in the static device, the positive and negative sequence impedances are equal. So in both the cases both are equal, but whereas zero sequence impedance are greater than the positive sequence impedance. So these two are the point that we can means using while we are solving the sequence impedance of the power system elements. Now let us discuss the sequence network. This is the topic number 9 for this lecture number 3 of unit number 5. So over here you can see that this is the sequence network. So here we have considered one single line diagram of a typical power system. In power system generally we have generator, then bus bar, then transmission line, then the transformer, whether it is step up or step down as per our requirement. Then after we have the transmission line, then we have the bus, and then after that we have the distribution system. So again we have the bus, LT and HT distribution is there. So that's why this is our single line diagram of a typical power system. So for finding the particular sequence impedance, the element say in this questions in subjected to the current and voltage of the sequence only. So this is the sequence that will follow by this say line diagram. So whatever the generator will generates will transfer to the transmission line, and then after it will go into the bus bar, and then bus bar to the transformer, and then the transformer to the bus bar number 2, and the bus bar number 2 to bus bar number 3. So this is the sequence will follow by the this say typical power system. And with the elements operating under this condition, say the elements which are operating under this condition, the sequence impedance can be determined and say analytically or through the experimental test result. So by doing certain trial and error method, or we can say analytical method, we can determine the impedance of all the elements which are present in this power system, or we can say this network. Now say if we know the say sequence network, say sequence of the network, or we can say element, the complete positive and zero sequence network of say power system can be assembled. So yes, we can determine all the parameters of the each and every elements which are present in the power system with the help of the say sequence analysis, sequence impedance analysis. And these networks are say suitably interconnected. So yes, we have all the elements and the networks which are interconnected in the power system, because we are having the interconnected power system. And to simulate different unsymmetrical faults, so the sequence current and the voltage during the fault then calculated, from which actual fault current and the voltage can be found. So from that we can determine the voltage and current value from the say sequence current and the say voltage during the fault condition by the analytical or the experimental test result from the given typical power system. Now let us discuss the topic number 10, that is sequence network of the say unloaded generator, or let us discuss the unloaded generator, how it will behave. So this is the circuit of an unloaded generator which is say grown through the reactance. So yes, all the all the phases which are indicated with the reactances of the given line. So this is the Ia current which is transferring through, or we can say delivering by this generator Ea. So this is the current Ia, or this is called the line current. Now this is the Eb. So Eb is delivering this Ib current to this line, and this is the IC. So EC is delivering this current, line current, to this, and then this is the neutral current IN. Our neutral is grounded with the reactance Zn. So this is the potential ground at which we have the potential is zero. So let us discuss how this sequence network of say unloaded generator we can determine. So say unloaded synchronous machine, say generator or motor, which is say grounded through a reactance of say impedance Zn. So it is shown in this diagram. And Ea, Eb and Ec are the say induced EMF in the three phase. So whenever we rotate our rotor with the help of prime mover in the magnetic field, or means having the magnetic field, then the stator conductor will develop the EMF, and all the phases are say 120 degree aparted to each other electrically, and all the phases will develop its own EMF, say Ea, Eb and Ec. So when unsymmetrical fault occur on this machine terminal, say unbalanced current Ia, Ib and Ic flows in the line. So whenever unbalancing occur, so at that time this current value of the currents will change according to the say the elements which are present, or we can say which are connected to connected with each of the lines, and according to their impedance value, the current will change whenever the unsymmetrical fault occurs in this transmission system. Now if the fault which involves the ground say in current which is equal to the phasor sum of the say currents Ia, Ib and Ic. So yes, all the currents is addition of this current Ia plus Ib and Ic will equal to the ground current, and which flows to the neutral from the grounded via the reactor Zn. So yes, whatever the current which is transferring through this will be the addition of this all three lines, and it will transfer through this. So whenever such kind of fault occur, then the loop will created through the ground, and then current will flow like this. So yes, this is the current Ia, In, which is an addition of Ia, Ib and Ic whenever any say line to ground fault occur, or such kind of say condition arise. So addition of all these three currents will become the addition of the neutral current. So In will be the Ia plus Ib plus Ic. So this is the sequence network of unloaded generator. Now let us discuss the topic number 11, that is positive sequence network. So in the positive sequence network, we have considered one generator, means a system which are having Ea, Eb and Ec are the generating units, and the Z1 are the Z1, all the impedances are same Z1, which are connected with all the lines. So Ia1, then Ib1 and Ic1, because this is the positive sequence, so all the currents are Ia1, Ib1, Ic1, and this is the say simplified, or we can say single phase circuit of this given system. So in which you can see that Ea is connected with the Z1, and this is the line on which we are having the Ia1 current, and this is the reference bus, and between reference bus and this is the line we are having the voltage, that is Va1. Now the Va1 will be say Ea minus the impedance of the network. So that is, we have the impedance, that is Z1, and the current which is transferring through this that is Ia1. So the equation of this say positive sequence network, when if we want to find a voltage of this particular network whenever the unbalancing occur, or we can say unsymmetrical fault arises, at that time the Va1 will be Ea minus Z1 Ia1. And the positive sequence network for the synchronous machine can be represented by the source EMF on no load, which are which are not connected with the load, and the positive sequence impedance Z1 in series with it. So yes, this is the diagram which is indicating that all the elements which are connected like this, and the neutral impedance Zn does not appear in the circuit, because the phasor sum of IA1, IB1 and IC1 will be 0. So and no positive sequence current can flow through the Zn, so that's why Zn is not drawn over here. So yes, any and the since the it is say balanced network, so it can be drawn on the single phase basis. So this is the single phase diagram of the given system, and the sequence voltage that we have determined, that is VA1 is equal to EA minus Z1 IA1. So this is how we can solve the positive sequence network whenever the any we are solving the sequence impedance of any system. Now then after we have the zero sequence network, so in which we have the zero sequence network, it is indicated with Z0G, then Z0G, and that Z0G it is connected with the system, and the current which is transferring through this line is IA0, IB0 and IC0, and this is the single phase circuit of this. So this is the addition of this all the elements, that is that Z 3Zn and plus Z0G, which is common, and it is indicated as Z0. It is zero sequence impedance of this given system, and the current which is transferring through this line, that is IA0, and between reference bus and this line A we are having the voltage, that is VA0. Now let us discuss this diagram. So in zero sequence network, the synchronous machine on say three phase and single phase basis are which are shown in A and B. So this is the say three phase and this is the single phase. Now as the current flowing in the say reactance, or we can say reactor impedance Zn, say is the sum of zero sequence current, so all the addition of this current will become the IN of this given system, and the voltage drop caused by it will be the three times we have the voltage drop is IR. So here we do not have the resistance, so that is I into Z, and we are considering the zero sequence, so current is IA0, and which is transferring through this Zn, so that's why Zn, and we are having three phase, so that's why 3 IA0 Zn. Now voltage drop of each zero sequence from the terminal of the synchronous machine, so that is 3 IA0 Zn plus IA0 plus Z0, where Z0 is the zero sequence impedance of the given system. Now the zero sequence voltage of the terminal A, which A of the say synchronous machine with respect to the ground, we can write the equation like this. So VA0 is equal to say minus 3Zn IA0 minus Z0 ZOG, or we can say Z0G IA0. So this is the say equation for the zero sequence network, and we can use this zero sequence voltage equation while we solve the zero sequence impedances of the given system. Now let us discuss the negative sequence. This is our topic number 13 of this lecture, and this is the negative sequence. In this negative sequence you can see that the the impedances are say will become Z2, because we indicate this negative sequence with 2, and all the currents are say going towards the means system, that is IA2, IC2 and IB2, and this is the neutral which is not connected with the ground, and this is the single phase circuit of this negative sequence network. So the reference bus for the negative sequence network is also say neutral of the machine. So the negative sequence voltage of the terminal with respect to the reference bus is given as VA2 is equal to minus Z2 into IA2. So this is the negative sequence network equation that we can use to solve the sequence impedance, or we can say we can determine the voltage of any negative sequence network whenever we have the unsymmetrical faults in the system. Now let us discuss topic number 14, that is sequence impedance of the transformer. So how this will we can consider. So let us discuss how this will we can indicate that the positive sequence series impedance say of a transformer is equal to its leakage reactance. So therefore the say resistance of the winding is usually small in comparison to the leakage reactance. So this is the say means main aspect of this negative sequence network for say transformer. Means so the transformer say being say static device that we all know, and the positive and negative sequence impedance is say is identical, because the impedance is say independent of the phase order. So therefore the provided solution, or we can say the applied voltage are say balanced, and therefore the transformer having the impedances say positive and negative sequence impedances are equal to the leakage reactance. So Z1 is equal to Z2 is equal to Z leakage. Now in this, so we can indicate it with say positive sequence, negative sequence, and say means positive and negative sequence impedances which are equal to the leakage reactance. So in this situation with say the three phase transformer is say more complex with regards to zero sequence impedance, because here the possibility of the variety of the connection in this power system, we are having a say interconnected power system. So we have say variety of the connection in the system. So assuming such transformer connected to the zero sequence currents which can flow on both the sides. So yes, we can consider this point over here. We can say that the zero sequence currents can flow in both the direction of the say transformer, and a transformer offers a say zero sequence impedance slightly different, which different from the say positive sequence impedance, but the difference is so small that the zero sequence impedance can be assumed equal to positive or negative sequence impedance. So over here we are having this effect of zero sequence, it is very small compared to means compared to a consideration. So that's why we have considered that zero sequence impedance means we are assuming over here which is equal to the positive or say negative sequence impedance. So that's why we have not indicated the zero sequence impedance over here. So that's why Z1 is equal to Z2 is equal to leakage is the sequence impedance of the transformer. Now these are the certain connections that we can do for in the do in our power system for the transmission of the power from one end to other end. So in this you can see that P is the primary and this is the Q is the secondary side, or this is the symbol in which we are having say a star which is grounded over here. This is also a star which is grounded. So this is the connection diagram of the given system, and this is the zero sequence equivalent circuit of this. So in which you can see that the three Zn and Zh, Zl and Zm are the reactances of the line, and this is the say neutral of the impedance which is connected with the P and Q, that is 3Zn and 3Zn with the Q over here. So this is the symbol, and from which we can determine the zero sequence and positive sequence and negative sequence impedance of the given system. Now let us discuss the second symbol, that is having one system which is grounded and other system is floating. So over here you can see that the impedance which is not affected over here means not indicated over here for the Q, which is connected in the previous case, that is 3Zn. So it is not connected, and Q terminal is floating over here, you can see that, and rest of the impedances are same as the previous case. Now let us discuss the third case in which we are having both the transformers which are connected in delta, but both are not grounded. So we have considered that the P and Q both are not having the say negative sequence or we can say sorry zero sequence impedances. So over here you can see that only we have considered the ZH and ZL impedance of the system, and in the fourth one you can see that the P and Q P is having a star connected connection which is grounded. So in this you can see that the primary is in star and which is grounded, and the delta which is the secondary. So in this you can see that this is the connection diagram which is shown over here for both the system, means both the primary and secondary, and over here you can see that this is the diagram of say the in the primary side we are having the 3Zn, but at the secondary side we do not have the 3Zn, means the zero sequence impedance is not considered over here because it is not grounded. So this is the diagram which indicates that the zero sequence equivalent circuit of this given system. And in the fifth one you can see that P is having star connection and Q is having the delta connection, and both are not grounded. So in that you can see that this is the impedance which is offered by the circuit when we consider we have when we calculate the zero sequence equivalent circuit of this given system. So over here you can see that 3Zn which is not connected with the P as well as the Q, and only the impedance which is offered by this circuit is ZH and ZL. So this is how we can connect the transformers in our very large power system, and we can say in our power system we are having the variety of the connection of the transformer for the different operations. So from this kind of different say connections, we can consider, or we can calculate the zero sequence equivalent circuit of the given system. Now let us discuss the topic number 15, that is sequence impedance of the transmission line. So in the transmission line generally we indicate with a single line. So over here you can see that 2 and 3, in between we have the transmission line, and this is the say reference bus and reference bus. And if we consider the positive sequence network, so as we all know that we indicate the transmission line with say R plus jx. So here we have considered only the reactance of the transmission line. So for the positive sequence network we will draw the say reactance with the name x1, and then we will have the negative sequence, it is x2, and this is the zero sequence, that is x0. So a fully transposed three phase line is completely symmetrical, and therefore as per the impedance which is offered by the it this is the offered by the transmission line is say independent of the phase sequence of the balance set of the current. So from that the transmission line in the entire three say sequence network is presented as the series network reactance element. So this is the series network reactance element that I already explained, and the impedance offered by it say to positive and negative sequence current is say identical. So therefore we can draw say original network in the positive sequence, negative sequence, and zero sequence by this way. So this is the sequence impedance of the transmission line. Now let us discuss the example based on the sequence impedance in the topic number 16 of this unit number 5, and this is our lecture number 3. So in this the in this given diagram, or we can say given system, you can see that we are having a generator 1, and it is connected with ground, and then after we have after the generator we are having bus number 1, and bus number 1 is connected with say transformer number 1 T1. So it is say having a primary is in delta and secondary is in the star, and the star is which is grounded, and then after we have the bus number 2 which is having a parallel feeder connection. Line 1 and line 2 both are transferring from bus number 2 to bus number 3, and after that bus number 3 we are having the transformer number T2, and T2 is having both connection are in star and both are grounded, and which is connected with the bus number 4, and then after we are having the generator number 2, and also the star connection of the generator is grounded. So all the say reactances of the say given generator transformer and the line is indicated or written in this table. So this figure shows a power system network which draw the positive, negative, and zero sequence say network. We need to draw the positive, negative, and zero sequence network of this given system, and the system data is given as the generator G1 is having rating MVA, all are having MVA rating 11, and the ratings of all the generator 1, generator 2, transformer 1, transformer 2, and line 1 and line 2 which are means written in this table. So let us draw the positive sequence, negative sequence, and zero sequence of this given system. So this is the positive sequence in which we are having both the generators are present, and all the means elements which are connected in say this is the sequence in which you can see that 0.25 over here. You can see that 0.25 is having the reactance 0.25 is generator number 1, and then after we are having say after generator we are having a transformer is rating is say 0.06 T1, and Then after we are having a parallel network, parallel means feeder, parallel transmission, or having a line 1 is having 0.1 and 0.1. This is the reactances of that. And then after we have the T2, that is 0.07. So this is the T2, 0.07 x1. And then after we will have the say reactance, that is J 0.2 for the given system, J 0.2. So you can see that J 0.2 is generator G2. So this is the reactance that we have written, that we can write from this given data for x1. Now x2 and x0, this will be used for the negative sequence, and this will be used for the zero sequence. So yes, similarly we can write the negative sequence as well as the zero sequence. And in zero sequence you can see that the transformer is having say 0.25. Then after we are having the one which is delta, and delta is not grounded, so at this point this portion is floating. And over here you can see that the both the transformers are grounded, so over here it is connected with the system. So this is the zero sequence impedance say of the given network. So this is how you can draw the positive sequence, negative sequence, and zero sequence. For that you can again say a recall, means again recall a theory of positive sequence, negative sequence, and zero sequence of all the elements we can that we have explained. And for that we have drawn the circuits for different variety of the connections. Now let us discuss the example number 2. In this the figure which is shown that shows that a power system network, which for that we need to draw a zero sequence network for this system. And generator 1, generator 2, transformer T1 and transformer T2, the MVA rating and the kV 11 kV x0 is 0.8 pu, and all the ratings are written over here. The data is given for the system. And zero sequence say reactance of the line is say 555.6 ohms. And this is the solution, and in the solution we have drawn a circuit, means a network of the given power system. So yes, you can see that at the primary side it is not grounded, as well as in the secondary side it is not grounded. Transformers T1 and T2 both are primary, and means primary is of the T1 and secondary of the T2 is not grounded. And this is the transmission line having the rate that is the rating is 220 kV. And say after that means transformer T1, we are having a rating that is 11 by 220, and the reactance of this transformer is 0.1 pu. And that for the T2 it is 220 to 11 kV, and the rating is 0.09 pu. So let us discuss the base MVA. And how can we discuss the base MVA? From the highest rating of the MVA rating, it is given over here 50 MVA, so we have considered base MVA is 50 MVA, and base kV is 11 kV. So yes, we can write the equation for x0 for G1. It is yes, we have the 0.08 that is given from in the data. And x0 for T1, so this is the equation that we can that we have already discussed in the previous case. So this is the reactance of the given given transformer T1, and this is the base MVA new to the old, and this is the kV new to the old. So this is the x0 of T1 is 0.1 pu. X0 of G2 is from after putting the values in the equation we will have the 0.117 pu. And x0 for T2 is 0.09 and multiplied with the base MVA is 50 and the old is 30, and 11 by 11 square by 11 square, so it is 0.15 pu. And for the transmission line, it is already given that transmission means zero sequence of the say reactance of the line is 555.6. So 555.6 will be multiplied with the new base MVA divided by its kVA rating, so it is 220 square, so it is 0.574 pu. So the zero sequence network which is shown over here. So all the parameters that we have calculated through this equations. And in the primary side and of the transformer T1 and the secondary side of the transformer T2, both are not grounded, so it is floated over here. And the reactance of the generators and the rest of the part is shown over here, which is calculated through this equations. So this is how we can solve the positive sequence, negative sequence, and zero sequence impedances of the given system. After that you have the assignment question, that is explain sequence impedance of power system elements in detail. and related to the related instructions which are written over here, please read it carefully. And if you have any query or doubt after this session, then we can solve your queries and doubt in our doubt solving session. And if any further query arise after watching, after going through this uh, presentation, then feel free to call me to solve your doubts related to the topic of this presentation, as well as if you have any query or doubt related to the say topics of the electrical engineering, then feel free to call me anytime. Thank you very much, student. Thank you all. Jai Swaminarayan.